You're all very welcome. We're nearly day 4 now, is it? Oops. Day 4 of our event. So thanks very much for coming along this morning. We appreciate that. We're talking about the ambitiously titled Solving Hybrid Cloud for High Performance Computing. So this is a non-trivial area, but we'll do our best with it for you. So by way of introductions, I'd just like to introduce myself first. So my name is Brian Farrell. I'm CEO at Securelinx, and this is my colleague, Owen Cotter. Owen is one of our senior enterprise architects, specializing in many things, including HPC with SUSE. And we're going to go through this in various levels of detail today. So I'll do the initial kind of high-level overview of what we're all about, and then Owen will take us into a bit more of a look at that. So just a little bit of background about ourselves. So we're based in Ireland, in Dublin, the capital city, and we've been working with Linux since the company was founded in 2002. So we've very much grown up over the last 17 years with Linux, and we cover all sorts of enterprise use case, and that was one of the real reasons we started the company. We wanted to make sure that we were bringing an enterprise grade of support locally to people within Ireland, the UK, and more recently that's developed across Western Europe as well. So within that, we've built out a very highly skilled team, including expertise around HPC. We have a very strong industry reputation, and the key relationships for us, we partner with the major Linux vendors, including SUSE, which is one of our key partnerships. So we're a SUSE solutions partner and training partner, which means that we cover all available options in terms of the portfolio that SUSE provides. And more recently, we've become a Microsoft Azure partner. So maybe 2 years ago, Microsoft came to us saying that they needed people with open source skills to help deploy various types of solutions within their public cloud. So within that, we've got customers in all sectors. So right through from central government, right through into education, academic, across financials, logistics, wherever there's a need for an enterprise Linux deployment, we work across that. And this is our nice shiny building in Dublin. So within those portfolio of things, we have a particular capability and interest in HPC. So HPC was one of the first areas that really commercially bit, where Linux commercially bit. It really was one of the big adoption areas back in the sort of early 2000s and even before that. So we're heavily involved in the design and delivery of HPC systems to multiple customers, in the architecture of that, right through to providing even managed services for those deployments. That includes things like third level escalation support, so we're really working well with the OSs that the issues the customers have. Occasions, if we spot bugs, of course we need to pass them up to the vendor, but it's a rare occurrence that happens. And our support provides everything from the infrastructure levels, so the systems, the storage, right the way through the OSs managing that, right the way through to application support, what the users are putting on top of that, and addressing users' concerns. And in many cases, this is one of the biggest challenges, because you're dealing with researchers, highly intelligent people in their field, and it's really important that we can relate to how those people work and what they need to do and get done. So what we're going to talk about today is a methodology and set of tools that has arisen out of some project work that we've done, and we feel it has an interest and lifespan beyond that particular project. Okay? So originally, what we were asked to do is to work and come up with some ideas for a customer that came out with a very technical RFP. So this client looked to have a HPC as a service offering, whatever that meant, okay? Because that can mean loads of different things, okay? So they wanted a HPC as a service offering. It was very important that they could get data separation and security separation on their workloads, because they were going to be working with basically human identifiable data, and it was quite important that researcher A would not necessarily be able to see researcher B's type work. And they were also moving from a very distributed environment into something that they wanted to be centrally managed. And they wanted an integrated hybrid cloud capability. So there's the clue as to what might come later in our talk. Luckily, from our perspective, they'd indicated that they were quite open to working with open source solutions. And they had Azure pre-selected for their public cloud because there's an existing relationship with Microsoft and Azure. So from our perspective, we thought, okay, we'll come up with a solution and a design. And from our perspective, we were delighted. Our proposal was successful. We moved it to a technical POC, and it met all the technical requirements that they had, including all those researcher requirements that needed to be done as well. So I'm going to just very quickly, out of that, Owen is going to go into more detail about what that actual POC looked like and how we get to where we want to be in terms of having an offering for hybrid cloud connectivity. But effectively what it means is we have created some magic here using the scheduler modifications and some workflows which will allow your job submission to either run seamlessly either in a traditional HPC environment, whether that's in a private cloud, which is what we did with SUSE OpenStack, or out into one of the public clouds. Okay. So Owen is going to take you through a technical run-through of this. So basically he's going to cover in more detail the proof of concept architecture that we had. He'll talk about the hybrid cloud methodology we have, which is a sort of a number of steps, the tooling that's involved as part of that, how you go about scheduling workloads. He's actually going to show you how some of this works. So that's why I was encouraging you all to sit near the front so you can read the command line stuff that goes on. And afterwards, we'll do a roadmap of what we're developing and where we see this going. Okay, this is quite a technical thing, but Owen will bring us safely back in a little while to somewhere where we can hopefully do a nice Q&A. And very keen for it to be as interactive as possible. And hopefully you're all keen on HPC environments, with the possible exception of our last friend. Do you like HPC?
First time.
First time, yeah. Great. So you've come right into the deep end of the pool. So you're going to either sink or swim, but we won't let you drown, I promise, okay? So that's what we'll do. And with that, I'm going to let Owen talk about some of the POC in more detail, and then let's get into the real stuff. Is that okay? Perfect. Owen.
Great. Thanks, Brian. So this is the architecture diagram for the POC that we actually implemented. SLURM. No, this doesn't really show up on the screen. Okay.
I'll point.
So SLURM is the key piece. It was the scheduler that was managing all of the job scheduling, including launching all of the instances running on the cloud. On the on-premise side, we had our SUSE OpenStack cloud. This was running using Ironic for bare metal compute power. It's one of the important things for the researchers was that they would actually get the bare metal power from their hardware. They wouldn't be limited to just using VMs. We did have VM compute nodes that were acting as compute power. So there was researchers that were launching jobs to VM on KVM in OpenStack. Of course, we had our OpenStack controller. We had an admin server that was managing everything. And then, obviously, a key part of the POC was that the SLURM was also managing the instances running in Azure. All of this was back-ended by SUSE Enterprise Storage. So obviously that's Ceph. It was providing both RBD block devices for all of the OpenStack images, including all of the bare metal compute. Volumes were all stored in OpenStack and launched from there. But it was also being used as a CephFS. So the researchers had their sort of shared directories on top of CephFS, and that was accessible in both the on-premise environment and in the Azure environment as well. So and then there's a small sort of NFS volume being served off of the SLURM master, and that's being used for sort of home directories and config sharing amongst all of the instances. So coming out of that, you're like, okay, this is great. We have a scheduler that's able to manage resources and launch instances in on-premise clouds and in the public cloud. But can we take that a bit further? It's SLURM. It can manage the traditional HPC. So why don't we extend that from using our on-site? I have a traditional HPC and I want to go to the cloud. How do we do that? And it was really just a case of, well, we take a SLURM that's managing a HPC and we extend it so that it can run instances in the cloud. We put together kind of a methodology for how you would go, okay, here's my traditional HPC. How do we get to running instances into the cloud? This is our methodology. 6 steps. There is an arrow there.
It's here.
Yes.
I'll be the arrow.
There is a really big arrow. It goes from left to right. Doesn't really come up on the screen there. Pity. but it is important that it is a progression. You need to go across. So the first thing you need to understand is your infrastructure and connectivity piece. How am I going to connect my current resources, potentially running on-premise or wherever, into my bursting resources? How am I going to get into the cloud? After that, you're going to want to have consistent images so that when you launch an instance in the cloud, it has the same software and the same applications available as on the on-premise side of the equation. Because you're launching instances and then destroying them, the cloud is ephemeral, right? The instances don't stick around if you're not using them. So you need to ensure that when your instances boot up, that they get the configuration required and are able to connect back to the on-premise resources. Then, once you have all that solved, you can move on to your batch scheduler integration. So we're using SLURM for that. When the instances start up, they need to talk back to SLURM. But at the same time, SLURM also needs to be able to launch the instances in the cloud. So when the job is scheduled to run in the cloud, SLURM needs to be able to understand that and launch the instances in the cloud. SLURM also needs to be able to auto-scale them so that when another job comes along, it'll launch another instance or as required. And of course, we do need to put limits on that so that our users don't go and, hey, there's this cool resource that I can just launch as many instances as I want in. Let's submit a 1,000-node job. Why not? And then a month later, you get the bill, and you're like, oh my god. And then the final sort of key piece in all of this is our storage and our output. So the thing that the researchers need to understand is that they are running in a cloud. They're running in a data center that is, at a distance from where they're currently running potentially. So there may be challenges around input to the job and output from the job and keeping that. So that is an important step that you need to go through with your users and understand, well, how am I going to run in the cloud? How is it different? Hopefully, we've taken our 6 topics and broken them down into 3 or 4 areas, highlighted by the color changes here. Said about the infrastructure and connectivity piece, this is it's a consultative approach. Every solution will be different, every cloud will be different. You need to look at what you're doing now and how to best get that into your cloud. Yep.
Yes, going back to storage for just a moment.
Mm-hmm.
You're bursting to the cloud. How are you handling the consumption of large data sets? And is your SUSE storage solution, is that in line with compute? Are you using that for actual compute storage, or?
So in the POC, we use the set for compute storage. Yep. For loading into the cloud in the POC, we use blob storage. Blob storage in Azure, so object storage. So the researchers would preload their input data into the cloud and then pull it from there. Okay. So I have a couple of slides on this later on as well, so we can hopefully get onto that. So that's our infrastructure and connectivity piece. Then moving on, consistent images and boot time configuration, right? That's really, how am I going to get an image that runs in the cloud that looks like my current on-premise image, and at the same time, when it boots up, it will start up and connect back to everything. So that's, we can tie these together. Batch scheduler and automation, and autoscale. How will SLURM auto-scale our instances? If we can connect our instances back to SLURM, then we can have SLURM auto-scale them. So we've tied that together, and then again, output and storage. It's kind of a consultancy piece. Which cloud am I using? Are my researchers using large workloads, small workloads? What's the best way to get their data into the cloud? Let's take a quick look. So we'll work through these from left to right. We'll start off looking at the infrastructure and connectivity piece. Just to say on this slide, the infrastructure and connectivity and the output and storage, they're really consultative with your users. I'll talk a little bit about them and sort of what we found out when we were doing it, best practices. But our solution really covers the consistent images and the batch scheduler integration, just to say that. So, on the infrastructure piece, look at the cloud that you're going to go to, find out what the best practices are for that cloud, and really follow them. Connectivity between the on-premise resources and the cloud is the most important piece. think about all of the services that your current on-premise resources consume. User authentication. I'm going to have like a shared resource. Maybe it's LDAP, maybe it's NIS. How will my cloud resources consume that? They'll need to talk back to the scheduler. If you're using an orchestration piece, they're going to need to talk back to the orchestration so they get the updated config, so that every time I change something, I don't necessarily need to regenerate all my images. It's actually pretty easy to do that if you want to, but we'll show that. But ideally, you have a bit of like, here's my image with all the software, and that's kind of complicated to build. And we'll when we boot up, we'll pull down the latest information. Storage. If you've got on-premise storage, how are they going to consume that? And DNS resolution is actually one of the pretty key bits, because you're going to be, when you're launching instances in the cloud, they will be dynamically created. They will get dynamic IP addresses and dynamic host names. So they need to be able to update your DNS with that, and the on-premise side needs to be able to resolve these in your DNS so that everything looks nice. Okay, yes. So as we said, we're going to try and demo this today. I'm going to only use Azure for the demo, but I am going to split the resources between sort of traditional resources and cloud bursting resources. So I have, you don't really need to know this, but if you're familiar with Azure, Azure splits, gives you the idea of resource groups in order to keep resources together and just to mine them in a big box. I'm using 3 resource groups for our demo today. We've got our traditional sort of HPC. It's completely static, nothing changes. I kind of lie here because I built everything using the same. Images as the cloud bursting piece. But for the purpose of the demo, it's a static HPC. Nothing changes. It's running in the north central US data region in Azure, which is up in Illinois, and our cloud infrastructure is all going to run in East US over in Virginia.
And I suppose just to say, so that's representing, this infrastructure could be representative of your on-premise HPC, just for this demo.
Yeah, so for our purpose of our demo, the north central US infrastructure is static and representative of an on-premise or existing cloud offering, and then we're going to burst into the East US data center. And that's actually a reasonably valid approach as well. Maybe the Azure region is particularly busy and you want to burst into multiple Azure regions. So this is our traditional HPC. It's got a lot of stuff in it. This is all reasonably static. We've got 2 compute nodes, TRAD1 and TRAD2, and we've got a master compute node up here, which is where our SLURM is running, and this is controlling all of the bursting into the cloud. We've got some other bits and pieces here as well. This is the infrastructure that we need in our cloud for the purposes of the demo. So this is in the East US side, and this is what would be permanently running in your cloud for the purpose of the demo. So we have an image, which is what our instances will boot from. We have a virtual network here. That virtual network is using Azure peering to talk back to the virtual network on our on-premise side, and we have a DNS zone as well. If you were doing this from like a different cloud or from an on-premise data center, you would also have like a site-to-site VPN or something here. Yep.
What DNS services are supported for the dynamic?
Anything that can.
For the dynamic record creation.
For dynamic record creation, anything that can do dynamic DNS. Okay. Yeah. And this is our cloud bursting resource group. There's nothing in it. We're gonna create all the resources in our cloud bursting resource group dynamically during the demo if everything works out. That's our infrastructure and connectivity piece. Moving on from that, we're going to talk a bit about our images piece and how we build those images that you saw in our Azure data centers. We're using a tool called Packer for this, Packer.io. It's from HashiCorp. You may have also heard of Terraform, which is another big tool that HashiCorp released. It's a free tool. It allows you to build automated images. So, and from that we can get, from one template we can get many outputs. So for, if we wanted to build templates for Azure, For AWS, for GCP, you can do a lot from that template. And this is what we used in our POC for all of our images. So same template was used to build OpenStack bare metal images, OpenStack KVM images, and our Azure images. It's got built-in support for all of the common orchestration tools like Salt, Puppet, Ansible, which is pretty handy as well, and most major vendor support as well. Is this the one? Yeah. So this is our image pipeline. We take our base images. The base image that we're using today is based on OpenSUSE 15, so OpenSUSE Leap 15, SP0. We've used other base images as well. Put all these into our image processor, which is Packer. We insert our configuration in on top of them, and then Packer goes out to the cloud and builds our images in the cloud. One of the nice things about Packer is that it builds the image in situ. So it takes the base image, which needs to be sitting in the cloud, and then processes it. So it starts it up, it spins up an instance from the base image that's in the cloud, applies all of our configuration to it, and then creates a new image in the cloud that we can then launch our instances from. And I have, I think, a quick demo at this point of that process. So
again, on those configurations scripts are stuff that we've written for this.
So those configuration scripts are bits that we've written for this thing. So let's take a quick look at our Packer template, which is our input. Let's make this a little bit bigger. Is that readable from the back there? Yeah.
Would you recommend incorporating applications into the image creation process, or providing them on a store that's accessible to the compute environment?
I would say that you would need to look at what you're doing and decide if you're going to do that. You could use this tool to create an instance per job type. Say I have a job that is going to be GPU, and I've got a bunch of GPU applications in it. I would put those into an instance, and when I launch my job, I would launch those on the GPU instances in the cloud. Equally, I've got like apps that are reasonably small and that can be loaded quickly. I would probably share those over like NFS over the cluster, or create a separate share in the cloud and keep all of those in sync. So yeah, it's an important thing that you need to look at and see how you're using in your environment. This is our image name. This is the output image. Let's just increment the version on that. Our builders these are the bits that actually tell Packer what images to create. So we've got two builders in this. Both are the Azure ARM type, and they've got separate names. One for North Central US, one for East US. These that's just decides where it's targeting. You can see we have our base image there. It's from SUSE. It's OpenSUSE Leap. It's 15.0, and this is our first builder that builds it in the traditional center. So this is what I use to launch the traditional nodes from. And our second builder is in it's targeting East US, and this is where our cloud infrastructure goes to. These are our provisioners. So these are how this is how we're configuring the images. Packer supports a number of ways of doing this, including like orchestration technologies like Salt. For now, we're just using direct upload files and some scripts to provision those files. So if I wanted to quickly make a change to that, I could add a file, say, to our. This is just where we collect all of these files and push them up into the image and unpack them. So if I just quickly wanted to add an MOTD, add that to our area that's tied up and sent to the image, and then I'll launch the image build. Plus drivers, image build. Let me just quickly show you how simple this is. This is our launch script. It's mostly just running Packer. It does the step where we want to tar everything in that anything directory up, and then we have another step inside our scripts that untar that in the build. We just run Packer build. I've got some template a variables file in there, so all of our secure variables are in there, like which our authentication credentials for Azure are in there. and then our template is down the end of the file there. So if we just launch that, and it'll go away. It'll do some checks, and then start building the image. Waiting for time, half an hour. We're going to let that run. I'm not entirely sure. Yep.
Did you look at possibly using the Kiwi application for your image creation? And
Yep.
if you did, why did you not select it? Just out of curiosity.
So it's a very good question, and I was chatting with some guys today. I was like, "Oh yeah, Kiwi. That's pretty cool. I could potentially use that." I just think.
Would have been my first thought.
Yeah. I mean, so when we went looking for a tool for this, it was very much for the hybrid. It was in the hybrid space. We're looking for an image pipeline. Needed to be able to support all the different clouds and quickly build images. And as I was saying earlier, one of the really nice things that Packer does is it builds the image in the cloud. So if I was using Kiwi, I'd build the image here on my laptop, and then I'd have to push it up into the cloud, right? That's complicated. Like, it is surprisingly complicated to get images into Azure. One of the difficult parts of that is that they require, so obviously they're Hyper-V. They require VHD files, I think it is. So that's the Hyper-V hard drive file type. And specifically for Azure, you need to have a 4 megabit block alignment in your file, so in your disk file. So in order to do that, you end up like converting your disk image like 2 or 3 times from your Kiwi output. I don't know how, I haven't, looking at this right, this is complicated. So Packer will just take an image that's already there, do some changes to it, and push it back into the resource group. So it's like, okay, that's great.
And the work is done.
The work is all done in the cloud.
Yeah.
There's no just geometry alignment.
There's no, the disks are created. So you see here, how far has it gotten? So you see this deployment group here is just dynamically created by Azure. So it's setting up these resource groups in Azure, and it's going to, from the source image, which is the OpenSUSE image, it'll deploy an image from there into these resource groups. Then it'll apply my provisioner steps to it, so my configuration will be applied to it there. The image will be shut down and captured and created as an Azure image, and all this is done, in the cloud. The only upload from my laptop will be those configuration files that I've scheduled for it to upload. So it's like, okay, it's like 140 megs a build or something currently.
So we have used Kiwi for other things, for more infrastructure-based projects, but Packer we thought was better for this particular need.
You're welcome. So that's how we build our images. The consistent, the boot time configuration is applied as part of our scripts. And the scripts know that when they're booting the instances, they need to call a certain script that has been added to the image. So let's move on while that's running and talk about our batch scheduler integration. So obviously we said we're using SLURM. It turned out to be actually fairly easy to configure SLURM for this. So it was like, okay, how are people doing this? Right, they're using power management features to extend SLURM to manage the cloud. So we think of our cloud images as compute nodes that we want to turn off when they're not busy. And we need to basically do 2 things in our SLURM configuration for this. We add the cloud feature to the nodes so that SLURM understands that the nodes will, not be there when they're off. And we configure sort of start and stop scripts that SLURM should use to start and stop the images. Yeah.
And that's just a resource tag within SLURM.
That's just a resource tag within SLURM, yeah, feature cloud. And then the start and stop scripts are what they're meant to be used for is to send IPMI commands to compute nodes, to physical hardware to say, turn this off, or this is the IPMI command to turn this back on. But the hard work in this piece was really sort of taking a script and then extending it to decide which cloud you wanted to start your node in, and then go and connect to that cloud and start up your node. And we sort of templated all this out so the same script is able to manage all the different clouds.
So as opposed to IPMI commands, you just have invocation commands to actually start.
Yep.
And then just tear down the VMs.
Yep, exactly.
Okay, cool.
We came across some stumbling blocks with that. So because you're running in the cloud, sometimes your nodes won't start. It's reasonably easily managed with timeouts. So you need to just ensure that your startup, your suspend time or your startup timeout is longer than the timeout that Azure or that SLURM will decide to run your job on another node. So that it's not, so the way SLURM works, it assigns your job to a node and then starts that node up, and then it waits for that node to start up before actually executing the job. As long as you have your timeout for the job to be, I think, lower than the startup timeout, then the job will move on to another node and try and start another node for that job. The other thing as well is that your resources do need to be pre-configured in SLURM. So you need to just define a number of compute nodes in SLURM. But really, that's okay because it adds a sort of an additional kind of quota step. If you only have 10 Azure nodes configured in SLURM, SLURM can only start 10 Azure nodes, right? So your users can't suddenly start those 1,000 nodes. Is this yeah. So we have just a demo of that. As you can see, our build is still running there. It's gotten onto provisioning steps, so it's almost done. So that's okay. We just won't be able to use that for our demo today. But let's move on. This is just a SLURM config file, just to point out that the changes are pretty similar. We have a counting setup. We have a suspend program configured here and a resume program, so that's for managing the cloud instances. We have some timeouts configured, so our SLURM timeout is half an hour. Our suspend time is an hour, so after an hour, we have no activity. SLURM will tear down our nodes. And we have our resume and suspend timeout set as well. Some log files, and then we've got some nodes defined. So we've got traditional nodes and our Azure nodes. And just the other thing to point out as well is that we have some suspend excluded nodes as well. So for all of your on-premise for your static nodes that you don't want to turn off and on, you just need to specify that these are static nodes. Yep.
Is it possible if you get to email that to me?
Yep.
Yeah, we can talk at the end about what we're going to do with this and making stuff available, okay?
And then we have two partitions configured. So we've got an Azure partition. This is where we, for instances in this partition, we will spin up new instances in our East US data center. We have our traditional nodes configured as well. So if you look at S info, you can see Azure. There's currently no nodes in our Azure. In our Azure partition, and our traditional partition has standard 2 nodes. So let's try and queue something.
Your build process is charging along the engine.
Yeah, my build process is charging on. It's doing an update at the minute, I think. No, it's doing OpenMPI drivers. Let me just check that we are going to launch in the right thing, because I was, of course, testing this yesterday. Yes, we are going to launch the right image. Excellent. And just so that, just to show us, this is the images I was showing you earlier. This is our traditional data center. This is the bursting center where all of our resources are going to be
empty at the moment.
Are going to be created. This is currently empty. If I do my queue into the Azure job.sh, that's submitted a bash job. This is just a simple script to what hostname am I running on, and sleep for 60 seconds. If I do SQL now, so you can see that's my job queued there. Where did that not? Is it -p? Yes. So okay, I submitted it to the default queue there by mistake. So now of course that job ran immediately on a traditional queue. For the job that we just submitted to our Azure partition, it's going to need a minute to spin up the resources. So if we take a look at this now, hopefully, there you go. So we're starting to see resources getting spun up there. That resource will come online. It'll contact back to the SLURM. We'll start to see it in sinfo there. So you can see that I'm using pretty small instances for this. They only have one CPU. So because I've got one job running in it, it's all allocated. If I was to submit another job, show sq-l now, so we can see now we've got an Azure 2 has been allocated, and if we come back to this, you can start to see that there. See the network security group has actually been created, so it does step through there. Yeah, there's our instance being created. Yep. The nodes would be deployed, and the job would get to the user would get access to the job.
Okay.
Yeah.
So previously, what's happened is we've been able to use this to connect jobs that were created within OpenStack out to Azure. But equally well, it will work with, as I say, your defined on-premise HPCs. And ultimately, like we've moved from one Azure data center to another Azure data center, and ultimately we hope to be able to move to other clouds as well.
And I understand the concept is to stretch the cluster to the cloud.
Correct, yeah.
I'm just trying to ascertain if all the expected functionality would be there.
Yeah, should be.
Yeah. So all of this was tested against a range of different workloads by researchers who all had different kind of requirements. So so far we found it to work well for everything that was needed.
Yeah. So you can see there, just as we've gotten to the jobs are running, we should be able to connect to those nodes now. Where are we? Still in the configuration stage, but I should be able to probably connect to that now. Interesting. That works. Okay, so still waiting for those nodes to come up and run the jobs. Maybe we can look back to that in a second, but just to show that the image build is now at the sort of the final stage. It's getting to the point where it's capturing the resources. It's completely configured them, and now it's capturing images. And we'll see those shortly in our Azure resource groups. Yeah, so actually it's done there now. So there's a final step where it just cleans up after itself. So if we look at, which one was that, East US. Yeah, so that's our East US data center there. And you can see the image that we just created is now available to be used by the instances. It's a simple config file change to have our scripts start launching instances from that image. It's probably taking slightly longer here because it's uploading files from my laptop over the wireless, but it is about a 15-minute process to actually build a new image in the cloud. That's essentially the demo piece concluded anyway. That's the SLURM configuration step. Is there anything else from that?
No, I think that's fine. I think we just go on to the other stuff, and we'll have time then for questions.
Move on. So let's talk a quick.
Sorry, are there any other questions at this stage? Can people follow what we did kind of okay?
Yeah, cool.
So we've gone through you've got some thoughts about how you connect to your cloud. We've gone through the image creation and the modification to the schedulers in order to connect these various things together. Yep.
So just some, I suppose, some quick ideas about storage. You do need to work with your users to understand the best storage that you're going to, the best way to consume storage for them. As I said earlier at the start, some of the work we've done with users has been to actually preload their storage into the cloud, so into Azure blobs. Something that's to think about if you're going to do that is that blob storage is limited to a certain number of IOPS. I think it's possibly about 5,000. Anyway, it's limited to a certain number of IOPS. So if you've got a lot of nodes running and you're trying to pull, data out of a single blob storage, and that might be quite slow. If your job can be parallelized and the storage can be spread out, even if it has to be duplicated across a number of blob storage accounts, you'll get better performance if you can tell your nodes to connect to different blob storage accounts for storage. Obviously, you can directly connect users to on-prem storage. I think that's quite fine for the likes of data load. Sure, if they're getting it into the blob storage from there, it can be done that way. Or if you have gone for sort of the third option here is to build a storage cluster in the cloud or build storage onto your compute nodes. So when you launch a set of compute nodes, use something like BGFS on demand to provision a parallel storage system underneath your compute nodes. It is important to remember, though, that if you're going to do that, all of your compute nodes will be running while you're loading storage. So that can get quite costly, especially if you've gone for the blob storage. I'm going to load from blob storage, and I'm only using one blob storage account. I've got 20 nodes trying to pull from the same blob storage account. It's going to take a while, and you're going to be charged for those 20 nodes. So make sure you're getting the best performance out of loading your storage into your compute nodes, especially if you're launching lots of them. Is there any? Yeah. So this is just to tie it all back together. We've talked about our infrastructure and connectivity, and we've talked about how we've shown the infrastructure that we've used here for the demo. We've shown the image build, consistent images, how it's important. Batch scheduler integration piece. SLURM has been able to launch our instances into the cloud, and we're able to auto scale those instances. So we can have as many as we want running at a single time. And finally, again, you need to consult with your users around the storage piece so that they get the best usage out of the cloud. Anything?
Yeah, go ahead. Yeah. So I guess in terms of, do you want me to give you a rest after your hard work there?
Thanks, Brian.
I have to mind the engineers at all times. So I guess our current state summary in terms of where we are with the solution. So right now, what do we support? We support from an OS point of view, we support Linux. In terms of clouds right now, so it's Azure, OpenStack, and within that we can do bare metal, through Ironic and other things, KVM and native. Our batches, from a processing point of view, is with SLURM, and the orchestration is done currently through the process kind of that you've seen, so it's kind of build and scripts, right? So right now, if our customers are asking us for this, it's kind of what I call a man in a van type service, right? So we have to bring some scripts with us, and we have to do some work in relation to that. But in terms of the roadmap, what we're looking at is having a better a rewrite and revamp of what we're doing, and an expansion as part of that. So we will have a much better system in terms of what we can deliver. So this is our kind of little an acronym for it. So it's the Securelinx Hybrid Cloud for HPC. We're going to be working with AWS and Google Cloud, and we're going to look at schedulers like PBS and Altair. So that will sort of come in as we move forward with this. And to some extent, this is kind of demand driven. So it's to do with the next project and the next thing customers might wish, or if people have specific requirements, we'll look at that. Sorry, beg your pardon. So what we're going to do in terms of moving forward is just to summarize that. In terms of that, we're going to open source what we've done. We're just going through what's the best processes for that once we have that. We're going to change our orchestration in terms of adding in sort of salt stack, which we think is a better way to move forward. And as I say, we'll be adding in the likes of PBS and Moab into our schedulers, and we're going to increase our connectivity to clouds. So that, in a nutshell, thank you, Owen, for bringing us safely back, as I promised you would, to what we do.
Yeah.
So I'm hoping that was of interest. It was great to have some questions, so thank you for those. As I say, right now, we've gone from a fairly complicated technical requirement to increase our usage of this, and we're very interested to kind of see what kind of feedback we have. And from our perspective, I guess, for a lot of people who have on-premise HPCs today, We've noticed over the long period of time we've worked with them that they tend to buy in sort of chunks of time. So, you know, they go out and they buy a big new cluster, and then they have to work with that for the next 3 years or so, maybe until the next funding cycle comes along. Whereas this is the kind of changes, and to add, you know, at a really effective cost point, to add cloud connectivity, maybe mid-cycle for some of those customers, and maybe leverage some of the new things that are happening within the clouds. So, for example, you may have bought your GPUs 2 years ago, and there's better available GPU type stuff happening in Azure, for example. Or you may want to cooperate with other companies or other research facilities and join together in a more constructive and working way. So that we think is quite a nice kind of mid-cycle option for some people to get an upgrade on what they're doing, and, you know, stay current until maybe they're in a position to re-architect or rearrange what they do in a more structured way as well.
Do you have a regular, when someone comes in and is going to start working with you, do you have a regular questionnaire that you use with them to help them determine what is good to extend to the cloud and maybe what they should be running?
Yeah, so I guess that is kind of a consultative type engagement, right? Where questions like that can be teased out. We don't really have I guess like anything, you know, I always use the analogy of the old, like, kind of what we'd call like a penny drop thing, that old game. So, you know, if you want it to come out at the end, it has to go through lots of little things. And there's various places it can get stuck where you know, requirements won't be met, and you won't quite get that alignment that you need. But as I say, we have worked with researchers in this mode who had very competing requirements, actually, in terms of their workloads.
Yep.
Maybe that's something to talk to a little bit.
So we looked at the POC was for a customer heavily involved in the bioinformatics space and general research in medicine. So there was a number of you know, like basically pipelines looked at. So there was one that was very batch scheduler intensive. So you just wanted to like run a bunch of jobs in the batch scheduler. There was others that were like entirely user driven. The user just wanted to be able to access additional resources. So we ran those outside of the batch scheduler, where the user was just we just created resources in the cloud for them, and they were able to log in and go, okay, yeah, that's I'm able to run my workload in the cloud. So what it is, you know, I would say take a look at your workload. If it's really highly parallel, it can really benefit from potentially running in the cloud. So see if I can get the numbers right here. As someone in Azure's HPC Black Belt team told me, if you can take a job that runs on 10 compute nodes and it runs in like 100 hours, say 100 compute nodes runs in 10 hours, right? Can you get that to run in 5 hours if you run on 200 compute nodes? If you run the same job, if it takes 5 hours in 200 or it takes 10 hours on 100, it's probably going to cost you the same, because it's just compute time. It's just how long the instances were running for. So potentially that's suddenly I have if I go to the cloud, I can get this done faster because my workload is highly parallel. So that's one type of workload to look out for. And yeah, as Brian was saying, the workloads that can make use of resources that are in the cloud that you may not have on premise, like GPUs. But yeah.
So it is. I mean, this isn't easy to do. I mean, so in some ways, the scripting and those pieces are kind of quite defined, and you can kind of match those up and improve those. But speaking with for the likes of, you know, a customer's particular requirements, and especially if it's say a research institute, you may have many different competing types of workloads. In some cases, that's very much a question of trying to define what those are and understand their ability to take advantage of something like this. But I like the idea of a questionnaire. I think that would be a great place to get to in terms of that. And we would certainly maybe produce a report for a customer about what they could look at.
Yeah, the storage is the key.
Yeah, that's kind of what I was wondering about. If it's at a certain level of storage, you just kind of say, maybe this doesn't fit.
Yeah.
Do you find any thresholds like that? Or?
No.
Not so far. Again,
No, we've customers who are using the cloud for like 3D, 4D surveys in the oil and gas industry, and they're really big. They're not bothered by that.
Yeah. So yeah, I think it is very much that hybrid message. You know, you have the option. You know, if you have your HPC on premise today, it's obviously doing what you want it to do. So this is like to see, well, what can't we do maybe on premise, or what could we do better if we had a connector? And I suppose that's where we see most people looking at stuff at the moment. I mean, there are people who go straight to cloud, and that's fine as well. We can work with those, but most of our current customers that we provide managed service for all have on-premise HPCs. So that's what we do. Is that okay?
Thank you
Anything
very
else?
much for coming.
Okay. Well, I just want to thank you. Sorry.